Okay, so in this unit, we will have the return of my ghetto physics demo. Okay, and we'll be looking at two things. Circular motion, okay, so any object that moves around a central point, and gravitation, because gravity often produces circular motion, okay, orbits, etc. Okay. So we'll be looking at that. Now there's a little bit of Newton's second law stuff in here, okay, because the whole reason that something moves in a circle is because of Newton's second law. But it's not at all like the Newton's second law stuff we did in the last unit. You're not going to be having to worry about like huge.
She wants to see that.
Exactly. Okay. Okay. We won't have to worry about like huge vector sum of all forces kind of problems or anything like that. Okay. It'll be quite a bit simpler than that. Okay. So we're going to look at what circular motion is. It's when an object moves in a circle. Okay. Okay. So we got that one. That one's easy. Okay. We understand how circular motion happens. That's a little bit different. Okay. And we have to understand the relationship between period and centripetal velocity. So this is a new term for us in physics. Okay. Period goes along with frequency. They are the inverse of each other. Okay. Period is represented by a capital T. Okay. Frequency by a lowercase f. Okay. Does a period usually represent a fixed amount of time? Yeah. Okay. Our class periods are 85 minutes long. Okay. The Earth's orbital period is how long?
24 hours or 3 hours.
Orbital period.
365 days and a quarter.
365 and a quarter days. Okay. That's why we have a leap year every 4 years. The leap year helps us make up for the quarter day that actually hit. Last year, wasn't it?
No, it's this year.
Was it this year?
No, it's next year. It's next year.
2020. It was 2020, yeah. Okay.
And what happens in a leap year?
In a leap year, we add an extra day to the calendar. February has 29 days in a leap year, right? And that's because the Earth's orbital period is actually 365.249 something, okay, days. Okay, so it's not 365 days, it's 365 and a quarter days. Okay, so every 4th year we come up with that, and then every 20 years there's an extra like 3 seconds or something like that. There's a lot of like little things that we have to add in here and there to make the calendar work. Because if we didn't, the calendar would be a mess, and we'd have summer and winter. Okay, like summer weather in the winter. Yeah.
It would take a while for it to get.
Oh yeah, it's. I mean, after even a few hundred years, you're going to notice it. Okay. When we talk about orbits and periods, I'll show you a video where it actually resulted in the Russians missing most of the Olympic Games in 1920 because they were using they were using the Gregorian calendar instead of the Julian calendar, and as a result, they weren't accounting for X number of days, and they showed up 7 days late for the Olympics. Okay.
Is there any like relationship to anything that like calendar where it's like a different year now or like?
Oh yeah, some cultures use the lunar calendar.
In Ethiopia, they use that.
Yeah. So
what year is it for that?
oh, I don't know. Yeah, I just know they use the lunar calendar instead, so they use the orbits of the moon instead of Okay. And the lunar calendar was more commonly used before we understood the mechanics of the solar system because.
Right.
You know, we didn't realize we orbited the sun. It looked like the sun went around us.
Yeah.
Right. Okay, so understand how circular motion, back to period and frequency. So period is the time for one rotation or one revolution or one orbit. Okay, we usually just say cycle. Okay, so period equals the time for one cycle. So it's going to have the same units as any other time measurement. Seconds, hours, days.
Does the T represent period?
Yes, T represents period. Okay, so it's the time for one cycle. So it would be seconds, days, hours, years, okay, whatever it happens to be, whatever's appropriate. Okay, frequency is cycles per second generally, but it could be cycles per hour or cycles per minute, okay? But it's the inverse. Instead of seconds per cycle, it's cycles per second, okay? Which we sometimes call hertz, okay? If you have ever used like any kind of sound equipment, okay? If you're using like the equalizer, okay? You can change which frequencies are amplified, okay? Lower frequencies are usually like the bass, so anything below 500 hertz would be, deep bass. Anything below 80 hertz would be the guy that drives by my house every once in a while. Does he drive by your house? He sounds like this. That guy? Yeah. Okay. I don't know if he drives by your house too, but okay. So yeah, anything that's really low frequency is going to be deep bass. Anything that's higher in frequency is going to be like high treble, so over 1,000 hertz or whatever. Okay. Yeah, hertz measures frequency, cycles per second, where period measures the time for one cycle. It all depends on what's kind of appropriate for a given situation in terms of which one we use. But as I said, they are the inverse of each other. So period is 1 over frequency, and frequency is 1 over period. That formula is on your formula sheet. Okay, how does circular motion happen? So if I want this tape to go around and around in a circle, okay, what do I have to do? I have to use my hands, okay? What is my hand doing to the tape?
Moving, putting force on it in
Okay.
opposite direction.
I'm putting a force on it. Which direction is that force acting?
Moving this forward. Backward.
Okay, let me ask you this. If I let go of this, what would happen?
It goes the direction where the arms go down.
Actually, it wouldn't slow down.
If you let let go and it's that way, we go that way. If you let go and it's that way, we go that way.
Okay.
So
If
wherever you let go or wherever, because it's attached to a string, so it has nowhere to go, so it has to go around you, right?
Right, so if I let it go, it's gonna fly off in
What direction?
a straight line, right?
Yeah.
Okay. Whose law is that?
Newton's first law.
Right, Newton's first law. So as soon as I let go of this, the force that's keeping it going in a circle is gone. And the object will obey Newton's first law, and it'll travel in a straight line at a constant velocity. So I'm whirling this thing around and around in a circle right now, okay, at a constant speed. Am I moving it at a constant velocity?
No, because you're going in different directions.
It's always changing direction. Okay, if it's always changing direction, that means the velocity is always changing. What do we call a change in velocity?
Acceleration.
Okay, and accelerations require,
Force.
right, a net force. And that net force is towards the center of the circle. I'm holding on to this thing. If I let it go, it'll fly off in a straight line. The only reason it goes in the circle is because I'm pulling it towards the middle. Okay? That's what we call a centripetal force. Okay? Center seeking is centripetal. Okay? Without a centripetal force, always pulling towards the center, always causing the object to accelerate towards the center, okay, the object would go in a straight line without that. Okay? Everyone okay with that idea? Okay, now let's have a little fun. Okay, is that making some sense? Okay. So, uniform circular motion means that the speed is constant, but the velocity changes, okay? And it's not the magnitude of the velocity, okay? The magnitude of the velocity stays constant, okay? What's changing about the velocity? Its direction. It's moving in a circle, so the direction's always changing. And even a change in direction still counts as an acceleration and still requires a force, okay? That centripetal force that I was providing with the string, okay, on the tape, okay? If that string was to be let go, okay, or to break, then the object would fly off tangent to the circle at that point in a straight line, okay? That's how David slew Goliath. Okay, the whole idea of the sling. Okay, the sling was just well, it was essentially like this, except it was made out of hemp, like braided hemp. Okay, and it had a little pocket in the middle where you put the stone. Okay, now with a sling, what you do is you have like a trigger knot, okay, that you hold between your fingers, and the other knot gets held here, and you whirl it around and around like this, and then when you want to let the string go, you just release the trigger knot. Okay, and at that point, the rock flies out in a straight line. It's kind of hard to do with the weight on the bottom. Okay, but if you have that weight there in the pocket, okay, it goes around and around and around, and when you let go of the trigger knot, it straightens and the rock goes off in a straight line. Okay, and it can go fast. Okay, you can make something like that, maybe not a rock, but certainly the end of the sling could break the sound barrier. Okay, the rock would be going close to the speed of sound when you let it go. Okay, which is pretty fast. I wouldn't want to get hit by a rock going 300 meters per second. Okay, neither would Goliath. He didn't have a choice. Okay, so it's certainly a way to increase speed. A sling does just that. Nobody can throw a rock that fast. Okay, but if you use kind of the mechanical advantage of something moving in a circle, you can make it go that fast. Okay. All right, so the big thing we got to get here is that that circular motion is a constant speed, but a changing velocity. Okay, that's the result of an acceleration. Okay, the vector on that velocity is always changing, but the magnitude is always the same. Okay, so when we're looking at the speed that something moves in a circle, we can use this formula. V equals d over t. Problem is, it's moving in a circle. So if it makes one complete revolution, what do we call that distance? The circumference. Right. Okay, so we substitute in place of d, the circumference of the circle, 2 pi r, or pi times diameter, whichever one you're given. Okay, we usually use radius. You're usually given radius in physics. Sometimes the question's trying to trick you, they'll give you diameter. Okay, and then we divide that by the time per one rotation, the period. Okay, so to calculate the speed of something moving in a circle, we go v equals 2 pi r, so 2 times pi times the radius, divided by the period, the time per one rotation. Okay, or, okay, since period equals 1 over f, and f equals 1 over t, could I substitute, so this is 2 pi r over t, could I substitute f in for t? I could, okay? Because right now, this formula is 2 times pi times r times 1 over t, which is the same as 2 pi r times f. Only the 2 pi r over t is on your formula sheet, okay? The t is 1 over f is on your formula sheet, so you're expected to be able to derive the second version, all right? So if I want to calculate how fast something's moving in a circle, that's how I do it. Okay? Those kinds of calculations are what allow us to figure out how far away planets are and stuff like that. Okay? All right, we will leave it at that for today, and we'll get into that a little bit more tomorrow.